some reason. We're almost a week behind now. That's okay though. Ask questions, all right? I'd rather make sure you guys understand it, or at least fool me into thinking you understand it, than try and race through the material and no one understand it, okay? So we're going to continue with torsion today, right? We started with this idea that we have this linearly increasing strain, right? Deformation in our shaft as we go from one end to the other because we have an applied torque, right? Because we have strain or deformation, we're going to have stress, right? Hooke's law, stress, strain are related. And so we end up with this stress profile across the cross section, right? Only talking about cylindrical shafts now, but that's all we're going to deal with in this class, right? So we have this linear stress distribution through the cross section where it's zero at the center, right? We developed really this main equation that tells us what the torque is relative to the stress in our shaft. The polar moment of inertia is essentially some geometric properties of the shaft, as well as the maximum radius, right? And we can rearrange that to calculate what is the stress in the shaft if we have a known torque, right, and known geometric properties. We could also figure out what the stress is at any radius based on the fact that we know that this relationship is linear, right, as we go from the center of the shaft to the outside of the shaft. Gave you a little cheat sheet about polar moment of inertia, right, depending if our shaft is solid or if it's hollow, if it's basically a pipe, okay. Knowing Hooke's law and now knowing some relationships for not only the shear strain, but the shear stress, we then developed this equation here that gave us what is our rotation of our shaft based on the applied torque and some of the geometry, right? The length of the shaft, the polar moment of inertia of the shaft, and then the shear modulus, which is essentially just the stiffness, right? Stiffness as it relates to shear versus our E, which is modulus of elasticity, which is stiffness due to axial loads, okay? And so we worked through this example where we could calculate based on a shaft with a known allowable stress, right? We could figure out an allowable torque, and based on that allowable torque, right, the maximum torque the shaft could handle before it reaches its maximum shear stress, we could figure out how far does that shaft rotate, right, in radians, or we converted it to degrees, right, 5.5 degrees. But that shaft would rotate based on the applied torque, the length of the shaft, and the material properties and cross-sectional properties, okay? So today we're going to start with another example, all right? In this case, right, this type of setup is very common, right, where we are transmitting torque to different, say, pulley assemblies or different mechanisms that we're using, right? It might be gears, or in this case we have pulleys, right, where we have torques coming and going out of this shaft. So really, over this problem statement, okay, we have a two-segment shaft, right? There are essentially two different shafts, shaft 1 and shaft 2. Power is input into shaft at B, right? So the center of the shaft, we have input power, which we're going to talk about power here in a little bit. Maybe not today, but Monday for sure. Okay, they tell us that the torque that's applied at B is 260 Newton meters. They have a torque at A of 90 Newton meters is removed from the shaft at A, and a torque of 170 Newton meters is removed at C. They show us the directions of these torque. They say that the shafts are made of a certain material, right? They're both solid shafts. They're both made out of bronze. They give us two different diameters and two different lengths of each of those shafts, right? L1 and L2. And diameter 1 and diameter 2. And they want us to determine the rotation angle of pulley C relative to A. So what does that mean? Well, that means, right, they want us to find, really, our phi of C, the rotation at C, relative to the rotation at A, right? So we're going to need to step through this shaft and see, okay, how much rotation do we get out of the first shaft and how much rotation are we going to get out of the second shaft, right? Well, to start out with, okay, I'm just going to do an overall equilibrium check, making sure that the power in equals the power out, right? If it's not, then this shaft is going to be moving. So we have overall equilibrium check. Well, in order to do that, I'm going to just sum moments about point A along the x-axis. So we're going to sum moments about the x-axis. That has to equal 0, right? Well, if we look at the direction shown for our applied torques, right? The torque going in and torque coming out. If we look at torque at A using the right-hand rule, my thumb is going to be pointing in the direction of the x-axis, right? To the right. So that would be a positive torque A. Torque B, right-hand rule, points to the left, which is in the negative x direction, right? This is our coordinate direction, x, positive to the right. Well, my thumb lands to the left, so it's going to be negative torque at B. And then finally, we're going to have a positive torque at C, following those same rules. Well, if we apply our actual values that were given, right, we have 90 Newton meters at A, 260 Newton meters at B, and 170 Newton meters at C. All of those equate to 0, so that's good. They gave us reasonable, right, torques applied and removed from our system. Well, in order to find the rotation, right, our equation for rotation, right, phi is the torque times the length divided by the shear modulus times the polar moment of inertia, right? And if we're trying to figure out, well, what's the rotation angle, right, phi, we need to know all of those things for each of our shafts, right? So we need to know the torque, the length, the shear modulus, and the polar moment of inertia. Well, the shear modulus is given to us based on the material, right? This is bronze, so it has 42 gigapascals. The polar moment of inertia, well, we can calculate that. They told us they're solid shafts of a known diameter. Okay, so J is known. The length also, they gave us L1 and L2. So really, the thing that we're missing is the torque in each of our shafts, right? So now, we need to look at internal torques, right? How would we do that? When we try and find internal forces, what do we usually do? Draw a free body diagram, right? Yeah. So we can cut out, right? We want to know what this torque is in shaft 1 and shaft 2. So us, right? We can step in here and we can take a free body out of this anywhere we want. And so in order to highlight, say, the torque in 1, I'm going to cut a free body out of this whole system. That includes the torque at A and the shaft 1, right? So what does that look like? So I'm going to cut out pulley A. Well, what does that look like? Well, it looks something like this. All right, there's our pulley A. Right. We cut it out. Well, we have some known forces, right? We have the torque at A that's applied. Well, knowing the right-hand rule, right? We know that our torque is a double vector or a double-headed arrow, right? We know it's going to go in this direction. I'm going to assume, almost forgot, right? Assume a coordinate direction in our free body diagram. I always want to do that. So we have our pulley at A, and we know that we have our torque at A based on the right-hand rule, right? The torque is going to be acting on the positive x direction. But we also have to have a resisting torque, right? This has to be in a state of equilibrium, right? So any torque we have to the right has to be acting to the left. Well, I'm just going to assume a direction for this torque that's acting in the shaft, right? Shaft 1 can act off to the right. So I'm going to now use my equations of equilibrium. I'm going to sum moments about the x-axis, right? All of these forces act along the x-axis. I'm going to sum the forces or the moments about the x-axis and set that equal to a, or set that equal to 0. While following our coordinates, that vector TA is acting in the positive x direction. So I'm going to say TA plus T1 must equal 0, right? T1 is also positive. So T1 is minus 90 Newton meters, right? Because TA was 90 Newton meters. So you plug TA into there, you're going to get that T1 is negative 90 Newton meters. What does that mean? That just means that the direction I assume for this is actually in the opposite direction, right? Which makes sense looking at that free body diagram, that if you have one torque, right, that vector heading to the right, we're going to need one that's heading to the left, right? Well, now that we know T1, we're also going to want to know what T2 is, right? I'm going to do the exact same thing except for on the opposite side of my assembly. I'm just going to cut out a free body, right? You could, if you wanted to, right? For segment 2, you could have cut out all the way to there, right? I could have drawn a free body diagram that had TA and TB and then cut through the second shaft, right? And I could have put a vector there establishing our, but I decided to cut that right-hand side, which is totally legal, okay? So we're gonna cut out pulley C now. What does that look like? Well, very similar to our pulley A free body diagram. Well, now if we look at that, right? TC, right-hand rule, our vector is pointed off to the right, right? This is pulley C. So if we have our applied force, right, our applied torque at C, it's going to be acting in this direction. We need to make sure we have our coordinate direction established, right? I'm going to say positive to the right. I'm also going to apply a vector now to the left in 2, right? This is the internal torque that's going to be in shaft 2. I'm going to sum moments about the x-axis, right? Got to label this. This is T sub C minus T2 equals 0. Well, that means TC equals T2. That means T2 equals 170 Newton meters. Yes?
This might be unnecessary, but I'm confused on why it's called taking moments.
Because a torque is essentially a moment, right? It's a force over a distance, right? Perpendicular distance to an axis. That's all it is. So it's in like the units of it are force times distance. So it's the same thing, right? You could sum the torques about the x-axis if you wanted to, right? But in general, in statics, right, the equilibrium equations we have are sum of the moments and sum of the forces. Well, when we sum moments, we sum them about some sort of point, right? We're looking at it perpendicular, right? An axis that's sticking out of the page. But because all of these torques, right, or moments act along an axis, right? That's where our thumb's pointing, is along that axis. We want to sum moments about that axis. Does that help? Okay. So if we were to draw a diagram now of what's going on between A, B, and C of our torque, if you remember, right? If you remember, the sign convention for torque was if this vector arrow, right, is pointing away from the surface, then it's positive. If this vector arrow is pointing towards the surface, right, then it's negative. Okay? Well, based on our calculations on this free body diagram, T1 is actually pointing in the other direction, right? And if its actual direction is to the left, it's pointing towards the surface of this shaft, right? Everywhere we cut the shaft from the pulley at A to the pulley at B, the vector arrow in that shaft is pointing towards the end of the shaft. If it's pointing towards the end of the shaft, then this is considered a negative torque. So if we draw a torque diagram, it's going to do something like that, right? Negative 90 Newton meters. And the reason why it's negative is because the vector arrow is pointing towards the cut cross section, right? When we get to the pulley at C, right, or the shaft 2, right, that's going between B and C, if we were to cut any cut along this entire shaft, the torque vector arrow is always going to be pointing away from the surface, right? So this is considered a positive torque. So we got a positive 170 Newton meters, okay, in that shaft. Okay. Let's say that the sign convention, right, I don't want to confuse people, but it's good to know that there's a difference between a torque diagram, right? The torque diagram is based on the sign convention for torque, which is based on which direction is this arrow pointing on the cross section, right? Is it pointed towards the cut or is it pointed away from the cut? On the free body diagram, our sign convention is based on our coordinates that we established, right? So if this vector arrow is pointing in the positive x direction, then we consider it to be positive, right? T1 was positive here. Okay. So now we have, out of this equation, right, our angle of rotation, we have everything, right? We've got the torque, the length, the shear modulus, and the polar moment of inertia, right? Well, we'll have to calculate that, but we have everything we need. So we're going to say phi is TL over GJ. Well, we want to know what J1 is, right? They're not the same because our diameters are different. We know, based on the previous notes, right? Polar moment of inertia of a solid shaft is pi over 32 times d to the fourth. That means for shaft 1, that's pi over 32 times 25 millimeters to the fourth. Well, that's 38,350 millimeters to the fourth. We're going to need that. We're also going to need the polar moment of inertia of the second shaft. Well, that's pi over 32, as always, times the diameter to the fourth. In this case, we have 30 millimeters to the fourth, or 79,522 millimeters to the fourth. Right, so those are our two polar moments of inertia that we will be using in our rotation equation. Well, now it's just a lot of plugging in to calculate. So this is T1, L1, G1, J1. So we get, as I mentioned, right, negative 90 Newton meters. Negative 90 because that vector arrow is pointing towards the surface. $300 millimeters. This shaft L1 was 3 meters. Or no, 0.3 meters. Or 300 millimeters. Because our torque is in Newton meters, I want to 1,000 millimeters per meter. Oh, I want to change the torque. Sorry. I want to change this torque, right, to include millimeters. And so I multiply by 1,000. I was looking at the wrong section. It seemed wrong. But I'm right. Millimeters per meter, right? All over G, well, we were told it was 42 gigapascals, which is 42,000 megapascals, which is 42,000 newtons per millimeter squared, as we know. So now we have J, which is 38,350 millimeters to the fourth. Right? Make sure you track units on these. We know that the angle of rotation is in radians, which is unitless. So all of the units in your equation, when you do rotation, should cancel. So, you know, meters cancel with meters, millimeters with millimeters, newtons with newtons, and the rest of the millimeters. Okay. What does that mean? Well, that means we get a negative 1.676 times 10 to the negative third radians for rotation. We can do the same thing for phi2, right? T2, L2, G2, J2. I'm not going to bore you with putting in all of that in light of time. So we're going to have 4.581 times 10 to the negative third radians. We're not done yet though, right? We have to figure out what is the rotation of C relative to A. So we kind of have to stand on this shaft at A, okay? And as we look down this shaft, right? Shaft 1 is going to have a negative torque, right? So it's going to be rotating to the left, okay? This torque A is essentially putting in a negative torque into this shaft. So it's going to rotate to the left relative to B, right? And then conversely on C, it's going the other way, right? So kind of the shaft is rotating one direction, and then on the other side it's kind of come back the other direction. So if we look at this in terms of our shaft, and we say, okay, A nice. So we start at A, right? And that shaft is going to rotate in one direction. We know the shaft's going to rotate opposite, right? The rotation of 1 is negative, right? Where the rotation in 2 is positive. So when we go from A to B, right? That's phi 1. We go A to B. We're going to do something like this, right? This is going to be phi 1. And we're going to be sitting now at B, right? And then when we go from B to C, we're going to have the rotation in the second shaft, which is opposite, right? So we're going to actually be moving the other direction. And because the rotation of 1 is 1.6, right? And then the rotation of 2 is 4.5, we're actually going to overcome the rotation that we just did, go to the other side of A and do something like this. And this right here is the phi A relative to C, right? That is the rotation that they asked us for. Is how far does C move relative to A? This might be because even though these two pulleys are pulling power off of the shaft, right? And they're, I guess, 0.3 meters on one side and 0.9 meters on the other side, right? These two might be connected somehow down the line, and there might be an issue with if A and C rotate too much relative to one another, we could screw up alignment down the line, right, with the mechanism that we're powering. And so in some cases, we might be very curious to know, well, how does pulley A twist relative to pulley C? So in order to do that, we're going to say that it's, right, phi 1 minus phi 2. Or negative 1.676 minus, or sorry, plus 4.581 times 10 to the negative third. We get 2.905 times 10 to the negative third radians. A relative to C.
Why is it plus the 4.581? You're subtracting.
Well, because they're acting in opposite directions, right? So this distance here is going to be the difference between phi 1 and phi 2. And so in order to do that, we end up subtracting the two from each other, right?
Is it A relative to C or C relative to A?
Oh, it's C relative to A, or A relative to C. It's about the same, right? If you fixed one, it would be the same thing. Okay. So now you definitely have everything you need to do the homework that I posted yesterday. Maybe it was even Wednesday. It's due this coming Thursday, okay? And we're gonna have a quiz this coming week as well, right? Wednesday to Friday, same sort of setup, okay? So don't procrastinate too much, all right? Now we're gonna talk about gears and torsional assemblies, right? Very common element, right, in shafts is to put gears on, right? Transfer cases, transmissions, I mean, you name it, especially on the MET side, right? Mechanical side of things. Very, very common. And we use gears and torsional assemblies to transmit torque and rotation, right? They allow us to change directions. They allow us to amplify torques, right? Change speeds, change rotation angles. And we're not going to look at like constant velocity transmissions and things like that, right? Gears, they transmit torque and rotation based on a fixed gear ratio. Right? So to start, we're just going to look at two shafts with two gears, right? Essentially two free body diagrams, right? This setup would look, right, if we looked at it in plan view, if we had gear B, and gear A, right? We have torque 2, we've got torque 1 as shown in the diagram. We've got gear A, we've got gear B. Gear B has some sort of radius B. Gear A has some sort of radius A, right? We need coordinates, so I'm going to say that's X, and this is X bar, right, or X prime. So that's what we have, right? 2 gears, mated, okay? They're at the end of 2 shafts, 2 different shafts. Each of these shafts have a torque in them, right? So if we were to split these gears, we could then draw a free body diagram, right? We have our applied torques. We know T1 and T2 and shafts 1 and 2, all right? We would also know that there's a force that's applied between, right, at this mated surface, right, between the teeth of our gears. That force we're going to call F, and that force has to be equal and opposite, right, in order to maintain equilibrium. Gear B is pushing on gear A the same amount as gear A is pushing on gear B, or B pushing on A, right? So this is a gear system in equilibrium, right? So we can sum moments in our free body diagrams, right? We can sum moments about the X prime axis, and we can sum moments about the X axis, and get a relationship between the radius of the gear, right, and the force applied F, based on the torque, right? So if we do sum of the moments about the X axis, we know that that has to equal 0, right? So now we're looking at the bottom gears there, gear A and torque 1. Well, torque 1 is acting, right, as we see in our free body diagram down here, right? Torque 1 is acting in the positive X direction, so we're going to put it in here as positive T1. Inversely, though, right, if we took the force, right, F of our blue arrow here, its moment arm is going to be R sub A, right? That's acting on this free body diagram. It's going to be acting in the opposite direction, so now we have a negative R sub A F, right? That means that T1 is really equal to F R sub A. And if we really wanted to know the force that's acting, right, at the edge of that gear where it contacts our gear B, we could say that that force is equal to the torque applied in the shaft at 1 divided by the radius of that gear, right? So statics, equilibrium, we can come up with a relationship between the torque applied in shaft 1 and the radius of that gear and figure out, okay, well, how hard is that gear pushing on gear B? Similarly, if we do it, same exact process, but now we sum moments about X prime axis, right? Now we're moving up to the free body diagram up above. We say that that equals 0. We're going to get negative T2, right? T2 is in the opposite direction from our X prime axis. Minus F times R sub B, right? Looking at that, we've got T1 acting in the negative X prime axis. Well, F that we have here is acting at a moment arm of RB, and if we use the right-hand rule, it's also acting in the negative X direction. So we get our equilibrium equation to look like that. Now we know that T2 is negative F R sub B. Well, we can substitute our expression that we developed for the force, right, that's applied between the 2 gears. We know that they're equal and opposite. They have to be. So we can say F is our T1 over R sub A, right? F equals T1 over R sub A. What does that mean? Well, that means T2 equals negative T1 RB over RA. Right? So a couple things you can glean from this, right? One is the torques are opposite, right? What does that mean? Well, we change direction. When we have a gear assembly, we change direction. We also know that the torques are related. By this ratio of our radius of our gear at B and the radius of our gear at A. Right? So if we want the torque in B, which is T2, right? We take the torque in the first gear, we change the direction because we know if we're using gear assemblies, it changes direction, and we multiply it by the ratio of the radius of gear B over the radius of gear A. So this ratio is just called our gear ratio. Okay. And in this case, we just looked at radii of our gears. Well, obviously, there's a lot of different ways in which we denote sizes of gears, okay? If you're into motorsports or even mountain biking, right? We've got gear teeth number. So you could say, right, we start out with our radius of B over the radius of A. Well, this is just a ratio of the size of these two gears, right? So that could be the same as saying the diameter of B over the diameter of A, or like I was getting at, right, number of teeth in B over the number of teeth. You learn how to spell teeth. Teeth at A, right? And this all is our gear ratio. Right? Anybody know what we're looking at in this picture?
Starter.
It's a starter, yeah. It's a starter on a flywheel. It's a flywheel on a lawnmower, okay? All right, big fancy lawnmower, right? If you're on a riding lawnmower, even I guess it's different for a non-riding, but if you have an electric starter on a riding lawnmower, okay, underneath the front hood, you see this big grill, right? It's always spinning, right? It helps cool the motor, it draws air down, okay? So this starter and this flywheel are essentially a big gear assembly, right? And there's going to be a relationship now based on the sizes of these two gears, right? The ability for this starter to apply a torque to the crankshaft of the motor, right? To turn it over to get it started. And we know from before, right? We have our torque at 2 equals the opposite of torque at 1 times RB over RA, right? Our gear ratio. That's essentially, as we know up there, if we did it in terms of B's and A's, it'd be torque at A times RB over RA, right? So in this case, when we have our starter gear and our flywheel gear, right, we're going to have a radius, say at A, and a radius of B, right? And because the torques are applied in opposite directions, right? TB is the opposite of TA times that gear ratio. Well, that means our rotation is going to be opposite. Right, so as you can imagine, if we were going to the torque applied at B, right? It's the torque at A times the radius of B over the radius of A. So if the radius of B is a lot bigger than the radius at A, right? The torque that's applied at A is going to be less, right? Because now, right, this ratio, right, if RB is, if the second gear is harder than the first gear, then our torque is going to be amplified. If the second gear is smaller than the first gear, then our torque is going to be reduced, right? So in this case, if you looked at this starter motor, there's a reason why this cog, right, this gear is so small, because we know that the force between these two gears has to be equal, right? So if the small torque is applied here, right, we're going to get a force maybe of 100 pounds over 1 inch, right? So this starter motor only has to apply 100 inch-pounds, right? But if this radius was, say, 5 times that, then the torque that it's going to be able to apply on the motor is 500 inch-pounds, right? So we're able to amplify the power of our starter motor in order to overcome the resistance of the motor to, overturn crankshaft, move the crankshaft. Well, this also plays true for the angle of rotation, right? Because we have a mated surface between these two gears, right? The forces are equal there. We also know that if this moves one gear, the pulley at B, right? The flywheel moves one gear. So if the starter motor, right, that interface rotates so that 5 gears pass, then the flywheel has to rotate so 5 gears pass. So we can also create a relationship between rotation again, right? That relationship is opposite because we have opposite torques, right? Same goes for, well, that's rotational angle or distance, which relates to distance. We can do the same thing for omega, which is rotational speed. Oh, these are opposite. Because when we look at this, right, as I mentioned, right, if this moves 3 gears, it's got to move 3 gears on the starter and 3 gears on the flywheel, right? And we know that arc length, as we talked about in the first example on Wednesday, right, is our rotation angle in radians times the radius, right? That would be arc length. And if this thing moves 5 radians, the distance that it moves on the outside of our circle is our radians times the radius, right? That gives us arc length. Back to geometry stuff. And so here, if we know that both of these gears move the same amount at this interface, right? 5 teeth, right? Or 5 inches. Then that means that the rotation of B times the radius of B has to equal to, right, rotation at A times the radius of B in the opposite direction, right? If this one's rotating to the left, we know this one's going to rotate to the right. So then that's where you end up getting this equation from. And once you have this equation, right, rotational speed is just that. It's the speed at which those are spinning. And so that relationship holds true. All right, so phi is angular rotation. Radians. This is angular, or I guess you could say just rotational speed. usually in radians per second. We'll talk about that a little bit more when we get to power, okay? So those are our relationships when you have a gear assembly. Well, sometimes we don't have gear assemblies, we have other assemblies, right? We want to transmit torque, transmit speed, change rotation, right? Sometimes we have a chain assembly. Motorsports, this is common, mountain biking, right? A lot of things, okay? We have chain assemblies. So, how does it change? Well, it changes the fact that now our rotation, right, if we had the radius of A and the radius at B, our rotation is in the same direction, right? And similarly, right, just like we had a gear assembly, if this gear moves 5 teeth, right? So it essentially moves this chain 5 links to the right. Then at that same point on the gear at B, right, it has to move 5 links to the right. And so we can come up with the exact same relationships, right, where we have the torque at B, but now our signs are the same, right? Torque at A times the radius at B over the radius at A. And then we have omega at B equals phi at B equals a phi at A times the radius at A over the radius at B. And we got omega at B, right, is the omega at A times the radius at A over the radius at B. Again, having this gear ratio that allows us to relate torque, rotation, and speed.
For your last two equations, is it R of B over R of A, or?
No, it's R of A over the R of B. Okay. And that goes back to, again, as I mentioned with the gear assemblies, right? If these two are connected with a chain, right, in order for them to continually be lined up, right, if you let go of one link on this gear, you've got to accept one link on this gear. So the distance that this gear moves at the edge, right, at the very edge of our gear, is the same on both of them. And so in order for that to be true, phi B times RB has to equal phi A times RA. And so I just divide the RB, which is opposite from torque. Okay. All right, let's start an example. Okay. So in this example, right, we've got a motor that's applying a torque, and we have a pulley shaft assembly that's going on where the motor's applying torque to a pulley of a known diameter, to another pulley of a known diameter, along a shaft to another pulley, right? And then finally we're going to take that out, right, at the very end of a gear, right, at E, okay? And what do they want us to find? Well, they want us to find T sub E, right? What is the torque that is produced at gear E based on the motor applying a torque at A, okay? And they gave us, right, the given here, the torque at A is 40 Newton meters. These can get very complicated pretty quickly, okay? But in general, my approach to these is always to step back and think about, okay, what is going on in the whole system? Like, what am I going to be expecting for the behavior, right? So I'm going to make assessment of the system. Just going to start at the motor, right? Well, the picture depicts it, but it's also provided up above, right? D sub A is 50 millimeters, and D sub B is 150 millimeters, right? So if D sub A transmit a force from a small radius to a large radius, right? We know that a small radius to a large radius is going to increase the torque, right? the force applied into this belt has to be the same on either end, okay? And our moment arm of that force is small here at the motor, right? And it grows as we get to a larger pole. And so I know that as we go from A to B, the torque should increase, okay? And we'll start working through that on Monday. Don't forget to start the homework, okay? I know you guys would love to do something over the weekend.